So, we will continue that problem, right. So, for the second iteration we have seen that your what you call power loss is 4.334 megawatt and Pg1 and Pg2 after second iteration 184.58 and 181.31 megawatt, right. So, now you have to check the mismatch that is the your generation minus your load or load minus generation, right. So, in that case delta Pg2 is equal to this is the total load and this is the loss we have obtained minus the sum of the generation 2 generator. So, we are getting delta Pg2 is equal to 8.414 megawatt, that means still not converged, right. Next what we will do using those data of the generation and all these things, right, whatever you have that you calculate using this I is equal to 1 to that your delta Pgi delta lambda iteration 2 you compute, right, using this value of lambda whatever you have got, right. So, in that case compute this term and this term, these two terms all have been explained previously, right, in terms of mathematical derivation. So, this is coming, this first part coming 2.72 and second part is 2.644. So, total is 5.364. So, delta lambda 2 will be delta Pg2 divided by this thing, right. Basically, this is df by d lambda is equal to delta Pg by d lambda dPg by d lambda, right. So, delta lambda 2 will be 8.414 divided by 5.364 is equal to 1.5686, right. So, this is change in that means in the your what you call in the third iteration, right, lambda 3 will take lambda 2 plus delta lambda 2, it was 107.59 plus 1.5686, right. So, lambda 3 is equal to 109.1586. So, for third iteration again you calculate using that same formula. So, Pg1 at the third iteration this is the lambda value minus 41 divided by 2 into whatever is there, right. You will get 188.849 megawatt in the same formula, just to substitute. So, Pg2 also at the third iteration 109.1586 minus 41 divided by 2 into whatever the parameters are here, right. You will getting 185.483, right. Sorry. So, that is your Pg1 and Pg2 after third iteration. Now, using these two generation values, right, your what you call compute the power loss at third iteration. So, this formula was given. So, point it is 405 into that Pg1 square, this is your Pg1 plus 0.408 into Pg2 square, right, this is the value of Pg2. So, here we are getting loss third iteration 4.535 megawatt, that means error is that is delta Pg3 370 plus this loss 4.535 minus the sum of the two generation which you have got, add it, right. So, delta Pg3 is 0.203 megawatt. So, this is also still not sufficient to low for convergence. So, what we will go, we will find out one more iteration. So, I is equal to 1 to this dPgi by d lambda third iteration, here directly I am writing the value 5.358, but you please compute, right, you please compute using this your what you call the value of your that lambda 3, right, please you compute this one. I am giving you the final answer, this is 5.358, right. Therefore, your delta lambda 3 is the delta Pg is 0.203 and your dPg d lambda summation is 5.358. So, this is coming 0.03788, right. Therefore, lambda 4 is equal to lambda 3 plus delta lambda 3. So, 109.1586 plus 0.03788, the lambda 4 will be 109.196, right. So, after this for fourth iteration you calculate Pg1 at fourth iteration, Pg2 at fourth iteration, substitute in the same expression, right, those values, you will get 188.95 megawatt, right, and this Pg24 you will get 185.58 megawatt, right. So, then with this you will get that P loss 4 again you compute using the same formula, that is P loss 4 is 4.54 megawatt. Now, check that error. So, delta Pg4 370 the load plus 4.54 minus sum of the two generation. So, this is coming actually 0.01 megawatt. This value is quite small and solution has converged, say, right. That means what? That this takes when you introduce this loss formula, this one takes more number of iteration, right. Here it is taking at least 4 iterations to converge, right. But gradient method has advantage that every iteration easily you can compute your delta lambda, and accordingly you modify the your what you call lambda and the generation, right, and losses. So, this is your final answer. So, this is your final answer. So, right. So, Pg1 is 188.95, this lambda is equal to optimal dispatch for lambda is equal to 109.196 giving rupees per megawatt hour, say, right. And this Pg1 is this much 188.95 megawatt, Pg2 is 185.5 megawatt and P loss is 4.54 megawatt. So, this is the answer after 4th iteration, right. If you want more accuracy you can go for further, but no need actually, you assume the solution has converged. Now, general method for finding penalty factors, right. So, although expressions seems to be big, but we will take small example to demonstrate this all this application, mathematical application. So, earlier I have told you that power loss is basically it is sum of the power injected at every bus bar, right. So, it is I is equal to 1 to n, it is sigma p I, right, is equal to sigma I is equal to 1 to m p g I minus your I is equal to 1 to n p l I. So, this is actually your power loss formula. Say this equation is say 70, right, and in this equation a nomenclature is also given. So, in this equation n is the total number of bus bars, right, m is the total number of generator bus bars, I mean buses where generators are connected, right. PGI is real power generation at bus I, this is known to you, and PLI the real power load at bus I, right. For generator bus I is equal to 1 to m, and for load bus I is equal to 1 to n, right, and Pi is the net real power injected at bus I, right. So, if we expand this equation, if we just hold on, just 1 minute, right. So, if we expand this equation, right, therefore, this one then we can write P loss is equal to this one, we can write P loss is equal to P 1 plus P 2 up to P n, right. This one we can write, that means your P loss is equal to P 1 plus P 2 plus P m up to the P m we are marking, actually it is up to that you have m number of generator bus, say up to P m, plus next one will be P m plus 1 plus P m plus 2 plus up to P n, right. This is that P loss, right. Now this equation, if you take derivative with respect to delta, this equation you take with derivative with respect to delta, then your what you call then dP loss by your d delta k is equal to, it is dP 1 by d delta k plus dP 2 by d delta k plus dot plus dPm upon d delta k, right, plus dPm plus 1 d delta k plus up to dPn by d delta k, it is equation 71. K is equal to 2 3 n, because delta 1 is constant is equal to 0 degree, right. So, we do not include k is equal to 1. So, this is k is equal to 2 to your 2 3 up to n, right. So, now for a given delta 2, delta 3 and delta n, we can compute delta P I upon delta k explicitly from the load flow equation. I mean, if you know delta 2, delta 3, delta n from the load flow studies, right, everything is known, then this one can be also computed, right. In general, it can be told that this is actually your what you call delta P 1 upon delta 2 k plus delta P 2 upon delta k. So, in general, it is actually delta P I upon your what you call that delta k, that is your, that means your P loss is equal to your I equal to 1 to n sigma P I, that means your this thing d P loss, then your, if we put in general d delta k, right, then this is actually your this equation can be written as your what you call that your I equal to 1 to n dpi d delta k, right. So, that is your what you call in for k is equal to 2 3 n, this way it can be written. So, that is why we are telling that dpi by delta k explicitly from the load flow equation only, right, because you have to know the load flow solution. Now, equation 71 this means it gives the expression for dp loss upon d delta k, right. Taking account for the relationship, we know Pgi is equal to net power injection, Pi is equal to Pgi minus PLi, but PLi actually is a constant, right. PLi is a constant. So, you take the derivative, you take the derivative this one with respect to delta k, your delta k, right. If you take the derivative of this one with respect to your what you call delta k, then dpi upon delta k will be dpgi upon dpi d delta k is equal to dpi d delta k. That means, you take the derivative of this equation, it will be dpi d delta k is equal to dpgi d delta k, because PLi is constant, right. So, note that is why I have written here also, note that PLi is a constant. Now, using the chain rule of differentiation, now you use the chain rule of differentiation, that means this equation, right. So, if you make it like this, that your what you call that dp loss upon d delta k, that means this equation we are writing, that is in general this equation dpi by d delta k is equal to dpgi by d delta k, right. At the same time, this dp loss by d delta k is equal to dp1 by d delta k plus dp2 by d delta k and so on, right. So, dp loss by d delta k, that equation can be written as dp loss upon dpg2 into, it is a chain rule, into dpg upon d delta k plus dp loss upon dpg3 into dpg3 upon d delta k plus up to dp loss upon dpgm into dpgm upon d delta k. So, it is chain rule of the differentiation, right. So, this way you can write for k is equal to 2 3 n. So, this is a chain rule, right. Now, using equation 73 and 72 we will get. So, in this case here it is your delta Pg2 upon delta k, delta Pg3 upon delta k in general, right, upon your delta your dpgm upon d delta k. So, because loss is a function of all the your what you call all the generations except the slack bus one, that is why this is written up to the mth term, because we have m generator, beyond that nothing, right. So, that is why it is starting from Pg2, Pg3 and up to Pgm, right. So, taking the derivative of that. So, in that case your equation 73 and if you look at this equation in general, it is basically you can make it dpg2 upon d delta k is equal to dp2 upon d delta k, dpg3 upon d delta k is equal to dp3 upon d delta k. So, this one actually you dpg2 upon d delta k, you can replace it by dp2 upon d delta k from this equation only, from your 72 only, right. Not again writing every term, but understandable in general, the dpgi upon d delta k is equal to dpi upon d delta k. So, here we are replacing this one dpg2 upon d delta k by dp2 upon d delta k, dp3 upon d delta k, from here only it is coming, replacing this one by this one, right. So, similarly, your dpgm upon d delta k is equal to actually dpm upon d delta k, again from this equation only, right. So, that is where it is equation 74 for k is equal to 2 3 n, right. So, this is your what you call the using chain rule of differentiation, right. So, next is, since the function P loss does not include Pg1, because P loss is a function of Pg2, Pg3 up to Pgm, right. Your Pg1 among its arguments, therefore, delta P loss upon delta Pg1 is equal to 0 and it is not included in equation 73. That is why in this equation it is not included, because P loss is not function of your Pg1, that is why it is Pg2, Pg3 up to Pgm, we have taken the derivative, right. That means that now you subtract equation 74 from equation 71, right. Now, let me find out 74, you have to subtract equation 74 from equation 71, right. So, for your understanding only, I am trying to write this equation, I am subtracting, right. First your what you call subtract it from equation 71. So, I am writing equation 71, right. So, hope everything will be readable to you. Just have a look. Delta P loss, then delta K, right, is equal to dP1 d delta K. I am rewriting that dP2 d delta K plus up to dPm d delta K. Next term will be dPm plus 1 d delta K, then up to nth term, right, plus dPn d delta K. This is actually your equation 71, right, and then equation 74 is this one. I am writing again that dP loss d delta K is equal to your dP loss dPg2 into dP2 d delta K plus dP loss dPg3 into dP3 d delta K plus mth term dP loss dPgm into dPm upon d delta K. This is your what you call equation 74, right. So, just for your understanding, actually I have written this. Now, you have to do is that you subtract your what you call equation your 74 from 71, right. So, what you will get if you subtract from this one, I mean this, if you subtract from this one. So, this one if you subtract 74, this time will be 0, right, left hand side will be 0. So, left hand side putting it on the right hand side 0. So, if you subtract that, first term will remain as it is, right, first term will remain as it is. So, that is here dP1 d delta K plus, right. So, you are subtracting 74 from 71. So, if you do so, then this term will come, that dP2 by d delta K you take common dP2 by, then it will be your dP2 d delta K, in bracket it will be your dP loss by dPg2, right. Next term, right, if you take similarly for the second term also, this way it will come up to your what you call up to the, because it is up to m. So, this is up to dPm, this is up to dPm, right. So, it will be your dPm by d delta K, right, in bracket it will be 1 minus dP loss by dPgm. So, it is up to your mth term, right, up to mth term. After that no other extra term is here. After that it will remain as it is. After that it will be dPm plus 1 by d delta K, so on. I mean it will continue up to dPn upon d delta K is equal to 0, right. That means we are subtracting actually equation 74 from 71. If you do so, actually we get, I have shown you how we are getting it. So, this way your what you call, we are getting this equation dP1 upon d delta K plus dP2 d delta K 1 minus dP loss dPg2 plus up to dPm d delta K 1 minus dP loss by dPgm, right. Then up to the mth term is okay, from here to here, I mean from generator 2 to your what you call mth one, you will get like this, plus in the equation 74 no other terms like that. So, it will be dPm plus 1 upon d delta K plus up to dPn upon d delta, that is equal to 0, right. So, this equation is 75, is for k is equal to 3n, right. Now, this is actually for your delta K, then k is equal to 3n. So, when you put k is equal to 2, you will get one equation. When you put k is equal to 3, you will get another equation. This way you have your what you call that your n number of equation, because it is going up to nth term, right. So, then what will happen, that if you put them in your what you call in that this term, if you bring it to that your right hand side, right, that means let me put it like this, otherwise again you may face problem. Suppose this equation is 75, this equation is 75. Now, this equation we can this term, this term is equal to, we will write minus dp 1 upon d delta k, right. That means, what we will do, we will write dp to d delta k, that is 1 minus dp loss dpg2, right, plus up to this one dpm d delta k in bracket 1 minus dp loss dpgm, right, plus dpm plus 1 d delta k up to dpn d delta k is equal to minus dp 1 upon d delta k. I mean, all these terms keeping to the left hand side is equal to, we are writing, that is equal to minus dp 1 upon d delta k, right. If and for k is equal to your, what you call, for k, this is for k is equal to 2 3, it will continue, right. So, in that case what will happen, k is equal to 2 3 n, it will be continuing. In that case you will get k, put k is equal to 2, k is equal to 3, k is equal to n, this way if you put, so you will get sets of your nonlinear equations, right. So, that means this equation, if we want to put in matrix form, this equation if we want to put in the matrix form, that means right hand side, that column vector will be del dp 1 upon d delta 2, dp 1 upon d delta 3, right. This way it will continue. So, and this one, this term, then dp 2 upon d delta k up to dpm d delta k, right, sorry, up to dpn d delta k, how we can relate to the matrix form. So, that means your this equation, that means this equation we can write that equation 75, this one we can write that dp2 d delta 2 up to dpm d delta 2, then dpn d delta 2. So, that dp2 d delta 2, its coefficient in 1 minus dp loss dpg2, that is here 1 minus dp loss dpg2. Similarly, its next term if you come, mth term if you come, this is his mth term, because to to accommodate this pages, I did not write all the terms. Next one will be dp 2 upon d delta 3 and so on, then it will come your dpm upon your d delta k, this thing, right. So, when it is coming dpm upon d delta k terms, right, it is 1 minus delta p loss or dpgm. So, your 1 minus dp loss by dpg2, then dot is come 1 minus dp loss by dpgm, right. That means, its next term will be 1 minus dp loss by dpg3, then next will be 1 minus dp loss by dpg4 and so on up to 1 minus dpgm term. After that, there is all the coefficient attached with this dp by d delta k in general, like 1 only, that is why this is 1 1 1, right. For example, if you for example, that this one your what you call this this dp 1 upon d delta k taken to the right hand side. So, that is why is equal to minus, it is dp 1 upon d delta 2, dp 1 upon d delta 3 and so on, then dp 1 d delta n. So, is equal to minus of this one, right. That means, this term has been taken to the right hand side, I showed you, right. That means, this is actually, it is that Jacob load flow studies we have done, no. So, there J1, J2, J3, J4 matrix is there, actually this one basically it is your J1 transpose, right. So, this that means, last one is dp2 d delta n up to dpm d delta n, then dpn. So, dp2 d delta n, dpm d delta n, right. If you do like this up to mth term, it is fine, right. After that is all coefficient, I mean dpm plus 1 d delta n, dpm your m plus 2 d delta n up to dpn delta n, these all are 1. So, this coefficient attached here as long as m up to mth 1, and after that all these things are 1 1 1 1, right, and these terms are here only, right, and is equal to minus dp1 d delta 2 like this, right. So, that means, in equation your what you call this equation 76 actually relate the bus powers pi to the angles delta k, and the matrix is just the J1 transpose. The load flow studies we have seen J1, J2, J3, J4. So, this matrix actually it is J1 transpose, right. So that means, after load flow studies you know everything. So, easily one can compute this our object, and this one actually, this is actually reciprocal of the, or what you call that penalty factor. Penalty factor in general we have taken Li is equal to 1 upon 1 minus dp loss dpgi, right. So, these are basically penalty factor. So, that means we can, if you know this, and if you know this, then easily you can have, then take the or what you call, you multiply by this J1 transpose inverse on both side, right, and then you whatever column vector you will get, you will find up to here term something will come, and after that your this one all will come to the right hand side also 1 1 1, right. So, that means that right hand your right hand side of equation 76 can easily be obtained, right, and from equation, and this is actually your what you call equation 41 of the load flow topic, right. That load flow we have studied, their equation 41 is there, right. So, from that you will get this, that equation 76 can easily be obtained after the load flow studies. So, now and it is actually, if you take the derivative of delta p 1 upon delta delta k, that is in general this equation, I mean this dp 1, this one dp 1 delta delta k, which I have written here, that in the right hand side this is column vector minus dp 1 upon d delta 2 up to dp 1 d delta n, right. So, this equation, if you equation 41 only, the load flow chapter, so is equal to mod v 1 v k, then g 1 k sin your delta 1 minus delta k minus b 1 k cosine delta 1 minus delta k, this is equation 77, and this is k is equal to 2 3 n, right. Therefore, thus it is very easy to find out the penalty factor using your equation 76, that means this one, that means from the load flow studies, after the load flow studies you know this, right, because this is J1 matrix and J1 transpose, right, and right hand side also this dpo, after the load flow studies all these parameters are known, your v and delta all are known, and g and b are line parameters, that also you know, right. Therefore, this is actually J1 transpose, and you multiply both side by J1 transpose inverse, right. Then what will happen, this 1 minus dp loss upon dpg2, then 1 minus dp loss upon dpgm up to this is equal to your minus J1 your transpose inverse into this one. So, a column vector will come, and from that you will find 1 minus dp loss dpg2 1 minus whatever m number of generator, this will find out, and this 1 1 1 is there, no, in the right hand side also, if that column you will see they will be 1 1 1, right. So, already that means this if you get, then whatever value you will get, its reciprocal will give you the penalty factor, because penalty factor is equal to the reciprocal of these terms, right. So, this is actually that how to find out the penalty factor actually from your this thing using that chain rule of differentiation and your from the load flow studies. That means, for this one to evaluate this you have to have a load flow studies. If you know the load flow studies and if you know the loss formula, P loss, that loss formula will after finishing this we will go to the loss formula, how to get the P loss in terms of Pg2, Pg3 and so on, right. So, that will derive today, right. So, these are the simple thing actually, only thing is that little bit of practice, right. As far as classroom is concerned, as far as classroom work is concerned, only 2 bus example is possible, right, or maybe 3 bus, one is a slack bus. So, not more than 2 into 2 in the classroom exercise, even very small example we can take. If you take bigger example, larger dimension size, then without coding we cannot do that. Thank you.